In this video, we're going to talk about numerical differentiation. Specifically, we'll talk a little bit about motivation in robotics, and then we'll discuss some formulas that you can use to take sample data and estimate the derivatives of a function from where the data came from. We'll talk about the errors. We'll talk about differentiation in the presence of noise, and then we'll look at some Matlab examples. So as we already talked about in our previous video, differentiation and integration are crucial parts in understanding how objects move, their position, what forces you need to apply to a certain object to get it from point A to point B. And this is an important element of robotics, particularly in high precision robotics, such as performing a surgery on a human being. Here you have a video of a robot arm demonstration to show how precise this can be and how it can help in different kinds of orthopedic surgeries, for example, right, where high precision is in demand. And like we mentioned, this is all about applying forces, about moving objects, about positioning certain instrumentation in the right place so you can perform the right interventions within a human body. So getting down to the nitty-gritty of the formulas, right, the starting point is Newton's formula F, which is a vector force equals mass times acceleration. So an instrument can apply a force to move the tip of the a robot can apply a force to move the tip of the instrument from position A to position B. We need to understand what forces can be applied to get the position to where you want it to be, and the position and the forces or the acceleration that are responsible for the forces are related to one another. And in our past video we saw how to take a function and integrate it, so you can, for example, go from acceleration to velocity, integrate it again to go from velocity to position. In this video we're going to cover the other direction, for example, where we can start from position, we can differentiate and element by element, right? So for example, if we take the x as a function of time and differentiate x with a function of time, we have the x component of the velocity. We do the same thing again, differentiate the velocity, the x component of the velocity with respect to time, and we have the x component of acceleration. This can be done element by element, and you have in the end a whole three-dimensional vector of position, velocity, acceleration. And how to go from position to velocity, velocity to acceleration is you can do this via differentiation. You actually have to do this with data to properly manipulate a robot. So here the objectives, more specifically what we're going to talk about in this video. We'll try to understand the application of high accuracy numerical differentiation formulas for equispaced data. We'll learn how to evaluate derivatives for unequally spaced data. We'll try to recognize the sensitivity of numerical differentiation to data error, and we'll look at a few Matlab examples. So in this slide, we begin by the intuition of how we can perform differentiation of a function based on measurement of certain data points. For example, here we have a function of an independent variable x that maps to f of x, which is called y in this case. And of course, let's say we have a quadratic looking function here, but in a typical situation, for example, in a robot, you don't have the whole function. Rather, you have measurements of certain things like position or force or acceleration at specific values of time. In this case, this is a function of x, but it could have been time as well, right? So you have f of x measured at certain points only. You don't have the entire formula for the function. Nonetheless, you have to have a notion of acceleration or differentiation so you can produce velocity acceleration vectors as well. So we're going to learn how to take just these black dots, which are the sample function, and compute something based on them that gives us an indication of what the derivative of that function at these particular points would be, or what an approximation would be. And the basic assumption here is that we're going to take what we typically understand of a derivative to be. The derivative is essentially a local slope, right? So if it's the tangent line, or this, if you had to approximate the slope, a function by a straight line at any given point, you would do so via the slope, and you compute the slope by taking a small displacement along the x direction, right? Evaluate the function at x plus delta x, subtract from x at that position, and then divide by delta x. Of course, the definition of derivative involves taking the limit of this delta x towards 0, and that's how you do it. Well, in numerical differentiation, we're just not going to be able to take the limit because we have the sample points, we have these measurements. The measurements, there's a limitation on how small we can make the delta x. So you get what you get, and you have to make do with that. So we're going to just compute delta y over delta x, and that will be sort of the intuition behind all of these formulas that we're going to look at for computing derivatives. So how do we, what's the more mathematical principle behind how we can derive these formulas? And this we're actually going to cover in the next video separately, but here we'll just talk about the intuition about how these formulas can come about. Step one is we take the Taylor series approximation of a function at a particular point, and this Taylor series will have the values of the function at that point as well as the values of the function in neighboring points, and we're going to manipulate these formulas to produce a number of approximation formulas for the derivatives. There are three main categories that we'll look at, and again the derivation of this will come in a separate video. But the three main categories for the formulas are what we call forward finite difference formulas, backward finite difference formulas, and centered finite difference formulas. So let's look to see what these formulas mean. Here is a bunch of forward finite difference formulas, right? Starting from a very basic one where you take, let's say you have your points xi, and you have I from 1 to n, for example. So the derivative of the function at xi will be, you take a look forward, meaning you take xi plus 1 and you subtract fxi and divide by h being the difference between xi plus 1 minus xi. Right? So that's the very basic, the first approximation formula. And there's a notion of error that accompanies this formula. Of course, this is not going to be the same as the actual derivative of that function, right? Will be an approximation to it. And you can ask what will be more or less the error between the actual derivative and the derivative computed to this approximation. And we write this as the error will be roughly the size of h, right? The step size, meaning I can make the error between the actual derivative and this formula for approximating derivatives smaller and smaller. All I have to do is decrease the step size, right? Meaning the difference between xi plus 1 and xi. In the next video, we'll show how to use these formulas to produce different ways of approximation. So the second formula here is another approximation for the first derivative, and it tends to be more accurate, but also it involves more different more values of the function itself, right? So, and this formula, particular formula, will be order h squared. For example, if you reduce the step size h, right, the error, let's say, h is it's smaller, let's say, than 1, right? So for example, h is 0.5. 0.5 squared is even smaller than h, right? So the error has been reduced by a power of 2. Right? We can apply these formulas recursively, so to speak, and not only obtain the first derivative, but the second derivatives, third derivatives, fourth derivatives, and so on. Right? We'll also see how to do this in the next video. Likewise, we can talk about backwards derivative formula, and you can look at the first formula here to understand what that means. Backward derivatives, let's say we want to estimate f prime, meaning the derivative of f at xi. Instead of looking forward, right, the past formula had fxi plus 1 here, now we have fxi, we subtract from the back the previous value instead, right? That's the only difference between the forward formulas and the backward formulas. We'll also see how to, and again, you can repeat this procedure for second derivative formulas, third derivative formulas, and so on. We'll again see that what this backward formulation really means in the next video. And you have another set of formulas which we call the centered finite difference formulas, where you can see the f of xi here is the forward minus the backward step, but now you divide by 2h. And this really helps because now the error is even smaller, h squared, right? Whereas before either the forward formula or the backward formula had order h here, now it's order h squared. So that's an even smaller error. And we'll explain again this derivation and the meaning of these errors in the next video. So all of this that we're talking about is for equally spaced data. For unequally spaced data, we can also apply certain formulas, and they are based on, let's say, the Lagrange Interpolation formula that we covered a few videos back, right? So you can fit a polynomial through unequally spaced data, and here's and once you have the polynomial, you can then differentiate the polynomial, right? So here you have the first derivative of this function. Now you can, once you interpolate, you can evaluate the first derivative at any point you would like. You don't have to evaluate the first derivative only at the grid point, right? So you can you have a little more flexibility in that way. So differentiation oftentimes comes at a little bit of a cost of accuracy, particularly if your data is noisy in some ways, right? So let's look at this example here in a little detail. Let's imagine we have this quadratic function, right? So this solid black line here is our quadratic function. That we would like to differentiate. Of course, we don't have access to the quadratic function itself. We only have access to these circle points here, right? That's what we have access to. Nonetheless, if the data points we have access are high fidelity, meaning they really correspond to the function, they have no error, no noise, we can still obtain an accurate derivative estimation via some of these formulas that we just covered. Right, so here you have the derivative of that function, which for a quadratic is a straight line, and you can obtain that. But let's imagine that either through numerical error, meaning your computer can only store numbers up to a certain precision because it's using a finite number of bits to store any real number, right? So let's imagine that there is a small amount of error in the sample values of your function. And even as you can see that these values here don't quite correspond to the quadratic function itself, but it's not too bad, right? So even a small little amount of noise can produce derivatives which are very different compared to the actual derivatives of the function, as you can see here, right? So one concept to keep in mind is anytime you take some available data, samples from a function, and you try to use some of these finite difference formulas to estimate the derivative of that function from the samples, if the samples have any amount of error or noise or something like that in them, differentiating the function can actually augment the errors on the derivatives than you would have obtained with respect to noise-free samples, let's say. So let's look at some functions in Matlab that can be used to differentiate. Matlab has certain built-in functions to help take derivatives of data values. So if you just call diff function here and you pass the vector x, which contains the values of your function evaluated at certain points, Matlab will produce the difference between consecutive adjacent elements in x. So you can use this diff, right? So let's say you have f of x or y of x, right? Which means a function f evaluated at some values x, you can estimate the derivative by dividing the difference, or the subtraction between adjacent samples in y over the subtraction of adjacent samples in x, right? That's our delta y over delta x formula. And that's the very basic approximation. That's the first order finite difference approximation of your derivative of the function y. If you have a two-dimensional function, right, we talked about the gradient just a couple of videos back, which is the derivative of a function with respect to x, and it's a vector of derivatives, right? The first element is the derivative of a function with respect to x. The second element of the vector is the derivative of the function with respect to y. That's called the gradient. So if you have a two-dimensional function and it's stored in an array called f here, and you have the step size in both directions where this function is sampled, you can just simply call the function gradient in Matlab, and that gives you the gradient. And if you just have one element here, you just get the first derivative. The differentiation with respect to the first variable. If you put two outputs, you actually will give you the two derivatives that you need to characterize the gradient of f. Matlab also has certain functions that help you visualize derivatives, specifically derivatives of variables in multiple dimensions, or gradients. And these are the contour function that we already saw, right? So if we have a function z that is a function of independent variables y and x, so these are all stored in arrays. As we saw before, we can call the gradient of z with respect to h. H is the adjacent, the displacement in x or y, so assuming they're both the same. And then there's the quiver function that can plot these vector fields, so you have a sense of the gradient. Right, so here's an example, here's a script. Some of you might recognize this as in our past videos as a quadratic function in two dimensions, f of x, y, right? And you have quadratic elements in x, quadratic elements in y. You have the mixed term here, and you have the y and x terms by itself. So here's a script where you can first declare a function like that. This is an inline declaration. You produce your grid of coordinates that way, and you then evaluate the function at those particular coordinates. So here's the code to do that. You then call the gradient of the function here. You use 0.25 as the increments in both x and the y coordinates, so you can pass h equals 0.25 here. You can plot the contour of the function, right? And that will be plotted in lines, in blue lines here in this case. And you can also plot the vector field of the gradient. So you have, in this case, we're taking the negative field, so it's, instead of the gradient pointing in the direction of greatest increase, it's going to point in the direction of greatest decrease. Right, so here's a quadratic function. The center here would have been the highest point, so the gradient should be pointing towards the center, but since we're plotting the negative gradient, it's the other way around.